Welcome to the autoionization of water and Kw. In the last video, we looked at a few examples of acids and bases. The example of a base that we looked at is NH3, ammonia, and we saw that when you put it in water, it acts as a Bronsted-Lowry base, meaning that it accepts a proton from the water, so it becomes NH4+. Accepting a proton is the same thing as saying accepting a hydrogen ion. And then we also got OH- as the leftovers of the water after it donated away that H+ to the NH3. An example of an acid we looked at was HCl. When HCl was placed in water, it acted as a Bronsted-Lowry acid because it donates a proton to the water. So the water molecule picks up the extra hydrogen ion, the extra proton, and becomes HO3+, and we have Cl- left over after the HCl donates away its H. Now in this lesson, we're actually going to focus on the waters and what they're doing. So we can see the waters in these two cases are actually doing something different. In the first equation, water is acting as a proton donor, so that makes it a Bronsted-Lowry acid. It donated a proton and donated an H+ to the NH3. In the second reaction here, it's acting as a Bronsted-Lowry base because it's accepting the H+ from the HCl. It's accepting a proton. And we pointed this out in the last video, how water can really serve two purposes. It can either act as an acid or as a base. And because of this, we gave water a special term. We said water is amphoteric. Because water can act as an acid or a base, it does something pretty interesting that we're going to take a look at in this video called autoionization. The autoionization of water essentially means that water is going to become ions. It's going to ionize. So it can become H+ and OH-. The auto part here means self. So this is self-ionizing. Water will become ions on its own. But why does this happen? How is water able to dissociate by itself or ionize by itself? And the answer to that has to do with what we just saw about water acting as an acid and a base, depending on the situation. And to really see this, imagine we have some sample of water. And in this water, we look at two particular molecules, one H2O and another H2O. And they're somewhat near each other, they even collide into each other. So here's two H2Os, they're going to collide with each other. Here's our particle diagram of the two water molecules. The H's are in green and the oxygen is orange. If one acts as a Bronsted-Lowry acid, so we'll say this one is going to act as a Bronsted-Lowry acid, and the other one acts as a Bronsted-Lowry base, that means that one is going to be donating a hydrogen, the acid one, and the other one's going to be accepting that hydrogen, the base one. So if we follow that reaction through, we'll see that one of these waters has lost a hydrogen. That makes it the OH- ion, whereas the other water has gained an extra hydrogen, and that's our H3O+ ion, the hydronium ion. So here I have hydroxide, and here I have hydronium. So you can see that the water molecules are basically ionizing each other. One of the hydrogens on the first water is attracted to the highly electronegative oxygen of the other one, and that results in this ionization, or autoionization of water. Now one thing to point out here, you'll see that I wrote H3O+ in the second reaction, because that more accurately represents what's physically going on with the water molecule. But it is essentially the same thing as saying H+, because one of the waters does release an H+. The one that acts like a Bronsted-Lowry acid donates away this H+, so it does separate like this. It's just that this H+ does not stay by itself for very long. It really will latch on to a water molecule to form H3O+. But in almost all situations, H+ is used interchangeably with H3O+. They have no difference in formulas and things like that. So these are completely interchangeable. Now, this autoionization does happen on its own, and it does happen regularly. But the particles don't last as ions very long. They actually reassemble back into the original water molecules very quickly. Because this doesn't happen very frequently, and the ions don't last very long before reassembling back into waters, you always have a very, very low concentration of hydroxide and hydronium ions in pure water. And because there's very low amounts of H+ and OH- in a solution, very low concentrations of these, that's why water is a terrible conductor, because it doesn't have a lot of ions present. Even though this shows that it has some ions present, in relation to the total amount of water, there's hardly any. So this makes it a very poor conductor. Now, because these reactions we just looked at for this autoionization, these are reversible, the products and reactants go back and forth, that means that they're going to arrive at an equilibrium position of some kind. There's going to be some equilibrium amount of reactant and product that ends up being in balance. So we can take a look at where that comes from by looking at the equilibrium between reactants and products. Because we know that this reaction goes to equilibrium, we can write a KEQ expression for it. And remember, the KEQ expression is always going to be products over reactants. So we have the concentration of H plus times the concentration of OH minus. So the product concentrations multiplied by each other. And we have to divide that by the reactant concentrations. However, the only reactant we have is water, and that's in the liquid state. And we consider the concentration of liquids and solids to be constant. So we don't really write a term under here, it's just over 1. So the equilibrium expression for this, or the mass action expression, is only H plus times OH minus. And because this is very special and has a lot of meaning for acids and bases, this has a special name. Instead of KEQ, we call this KW. And it's worth mentioning that this is the exact same expression as H3O plus times OH minus, which you could verify by just using the earlier equation we looked at. So at 25 degrees Celsius, the value of Kw is 1 times 10 to the negative 14th. So that means that the concentration of H plus and OH minus always have to multiply together to become this number. And we call this the ion product constant. This ion product constant is really useful. And just for an example, we can look at two things that it shows us. First of all, we know that when water dissociates, it forms equal amounts of H plus and OH minus. That's just from the stoichiometry of the balanced reaction. If there's equal amounts of H plus and OH minus, that means that in pure water, the concentration of H plus has to equal the concentration of OH minus, which equals 1 times 10 to the negative 7th. That's the concentration of each ion, because if you multiply this number by itself, you'll get the ion product constant. The other thing we can say is that say it's not pure water, say an acid or a base is added to water, that's going to change the amount of H plus and OH minus in the solution. But this has to maintain equilibrium. It has to be 1 times 10 to the negative 14th. So say I add an acid to this, that's going to increase the amount of H plus. But it still has to multiply together to become 1 times 10 to the minus 14th. That means the concentration of OH minus is going to go down. And they do this to maintain equilibrium. But this idea of one ion decreasing when the other one increases to maintain this constant ion product, that's going to be really useful in our next lesson when we talk about pH. That wraps up our lesson on the autoionization of water and Kw. Write down any questions you have in your notes and bring them with you to class.